Thank you very much for attending my virtual presentation. I would like to thank the ACS conference organizers for organizing this virtual conference. I would also like to thank the Physical Chemistry Division for the Journal of Physical Chemistry A Lectureship Award, which I was deeply honored to receive this year. Today I'm going to talk about catalysis on pristine two-dimensional materials through dispersion and electrostatic interactions. So graphene is a material that needs no introduction. We all know it's a sheet of sp2 hybridized carbons, and it has very unique physical and chemical properties. For example, a large surface area, high chemical stability, high conductivity, it's transparent, it's biocompatible, and it can be easily modified or functionalized chemically. These properties make it an ideal candidate for a number of applications. For example, in nanoelectronics, nanosensors, energy storage materials, and also in catalysis, which is the topic of this presentation. However, in current catalytic applications, catalysis normally doesn't occur on the pristine part of graphene, but at chemically modified or functionalized sites, such as zigzag edges, vacancies, heteroatom dopants, add atoms, or functional groups such as those present in graphene oxide. And a practical problem in the application and manufacturing of these catalysts is how to control the uniform distribution of these defects. So the current research started with a simple question. Wouldn't it be great if we could do catalysis on the pristine part of graphene, which does not have to be chemically modified or functionalized? But when you come to think about it, the pristine part of graphene has two unique properties that we can use to our advantage. It has a two-dimensional planar morphology, and it can interact with surrounding molecules through non-covalent pi interactions. And we will show today that we can use these two distinct properties to catalyze chemical reactions that proceed through a planar transition structure. In this work, which is mostly computational, we use large polycyclic aromatic hydrocarbons or graphene nano-flakes as models of graphene. The largest graphene nano-flake that we use has 96 carbon atoms, and the assumption is that at the center of this graphene nano-flake, we should have similar chemical properties to those of graphene. Now, we use very high levels of theory in this work. Normally, we use double hybrid density functional theory, and the computational cost of double hybrid density functional theory, along with the fact that we are modeling very large systems, means that these calculations stretched our computational resource to the absolute limit. So let's quickly get the computational details out of the way. We calculate our electronic energies with the REV DSD PBE P86 double hybrid density functional, which was recently developed by Jan Marten from the Weizmann Institute. This double hybrid density functional has been shown to give reliable results for large systems such as those we are considering in the present work. And we convert our electronic energies to Gibbs free energies at room temperature using enthalpic and entropic corrections, which are calculated at the DFT level. So all of the reaction barrier heights that we are going to look at today are calculated on the Gibbs free energy surface. So let's start with biaryls, such as the ones that we see here. And these biaryls can exist as configurationally stable axial enantiomers that can interconvert between each other through planar or nearly planar transition structures. So let's start with the most simple biaryl of this type, binaphthyl. Here we see the two axially chiral enantiomers that we have, and the transition structures through which they can interconvert. We have a syn-type transition structure and an anti-type transition structure. For the syn-type transition structure, we calculate an energy barrier of 140.9 kilojoules per mole, and for the anti-type transition structure, we calculate an energy barrier of 106 kilojoules per mole. So the anti-type transition structure is kinetically favorable. Now we have a fairly good agreement with the available experimental results, which are obtained barriers of about 100 kilojoules per mole. So we are not very far from experiment, which gives us more confidence in the levels of theory that we are using here. So how would these reaction barrier heights change if we placed a graphene nanoflake under our binaphthyl substrate? Here we will consider a fairly large graphene nanoflake with 96 carbon atoms. So a graphene catalyst reduces the barrier for the anti-type transition structure from 106 kilojoules per mole to 69.4 kilojoules per mole. Or in other words, the barrier is reduced by 36.6 kilojoules per mole, which is a significant reduction in the reaction barrier height. So how can we rationalize this reduction in barrier heights? One thing we can look at are the interaction energies between the catalyst and the substrate in the reactant complex and in the transition structure complex. So in the reactant complex, these interactions amount to 43.2 kilojoules per mole, and in the transition structure complex, they nearly double and amount to 79.8 kilojoules per mole. So we can see that in the transition structure, where both naphthyl units are parallel to the 2D catalyst, it maximizes the pi-pi interactions between the 2D catalyst and the substrate, and in the reactant complex, where only one naphthyl unit can be parallel to the surface, we have a smaller interaction energy. Okay, so now that we've seen how a graphene nanoflake can catalyze the racemization of binaphthyl, let's look at a more interesting biaryl, BINOL. BINOL is an important building block in organic synthesis, and it is used as a precursor for generating axially chiral catalysts. Here we see the two axially chiral enantiomers of BINOL, and again they are going to be interconverted between each other through a nearly planar transition structure. But perhaps more importantly in the context of the present work is that a recent paper in Angewandte has generated a large number of biaryl axially chiral biaryls from BINOL using dynamic kinetic resolution. In particular, they used a ruthenium-based catalyst to catalyze the BINOL racemization, and then a lipase for the kinetic resolution part. So in the context of this work, we can ask the following question. Can we replace the ruthenium catalyst with pristine graphene to catalyze the BINOL racemization? Let's examine the uncatalyzed racemization of BINOL. We obtain two possible transition structures for this racemization, a syn-type transition structure and an anti-type transition structure. Similar to the case of binaphthyl, the anti-type transition structure is kinetically favorable, and we obtain a reaction barrier height of 168.5 kilojoules per mole. This reaction barrier height is in reasonably good agreement with the available experimental data, which obtain reaction barrier heights of 158 or 165 kilojoules per mole. This again gives us confidence in the levels of theory that we are using here. For the binaphthyl racemization, we saw that the non-planarity of the reactant and the planarity of the transition structure were of key importance for the catalytic activity of graphene. So let's examine this in the case of BINOL. In the reactant, the two naphthyl units are nearly perpendicular to each other, with a dihedral angle here of 71.1 degrees, and the transition structure is nearly planar with a dihedral angle of 15.2 degrees. So we could expect that the BINOL racemization will also be catalyzed by a graphene nano-flake. For the uncatalyzed racemization, we obtain a relatively high reaction barrier height of 168.5 kilojoules per mole, and placing a graphene nano-flake catalyst underneath our BINOL reduces this reaction barrier height to 120.4 kilojoules per mole. Now, this reduction in the reaction barrier height is significant because it means that the uncatalyzed reaction will only be accessible at relatively high temperatures of over 200 degrees Celsius, but a graphene catalyst will make it accessible at much lower temperatures of below 100 degrees Celsius. And in a few slides, we will see why this is important for us. We can rationalize this catalytic activity by examining the interaction energies between the 2D catalyst and BINOL in the reactant complex and in the transition structure complex. In the reactant complex, we obtain an interaction energy of 31 kilojoules per mole, but in the transition structure complex, where both naphthyl units are nearly parallel to the 2D catalyst, it maximizes the pi interactions between the 2D catalyst and BINOL, and we obtain an interaction energy of nearly 80 kilojoules per mole. So overall, we obtain a significant reduction in the reaction barrier height by nearly 50 kilojoules per mole. We can also analyze the nature of the non-covalent interactions between the 2D catalyst and BINOL using an energy decomposition analysis. Here we are using the energy decomposition analysis of Martin Head Gordon, which is available in QChem. Here we see the interactions in the reactant complex, and here we see the interactions in the transition structure. We can see that both dispersion and electrostatic interactions are strongly stabilizing both the reactant complex and the transition structure, but they are much more pronounced in the transition structure, where both the naphthyl units are parallel to the 2D catalyst. We can also see that Pauli repulsion are strongly destabilizing both the reactant and the transition structure. But overall, the stabilizing dispersion and electrostatic interactions outweigh the Pauli repulsion interactions. This is perhaps the most exciting result that I have today: the experimental confirmation that a pristine graphene sheet will catalyze the racemization of BINOL. This is a very recent result that was just published in ChemPhysChem. So our experimental collaborator, Joel Hooper from Monash University, used chiral HPLC measurements to show that the BINOL racemization will proceed at 60 degrees Celsius in the presence of single-layer graphene in a water DMF solution, whereas the uncatalyzed racemization requires a much higher temperature of over 200 degrees Celsius. An experimental confirmation of a computational prediction is not something that happens every day, and we are indeed very excited about this experimental result. I also think that this experimental confirmation is very important for taking this catalysis by pristine 2D materials to the next level. Joel Hooper also obtained an experimental reaction barrier height for the graphene catalyzed reaction of 104.6 kilojoules per mole, which is in relatively good agreement with our calculated reaction barrier height of 112.7 kilojoules per mole in a simulated DMF solution. Now let's move on to something not completely different: curved polycyclic aromatic hydrocarbons. So if we look at C60 from this angle with a 5-membered ring in the center here, and we curve out the rings that are surrounding this 5-membered ring, we will get a fragment of C60 called Corannulene. And if we look at C60 from a different angle with a 6-membered ring in the center here and curve out the rings surrounding this ring, we will get another fragment of C60 called sumanine. And these molecules have very unique structures because they are bowl-shaped aromatic molecules. So the bowl has a depth. In Corannulene, the depth of the bowl is 0.87 angstroms. Sumanine has a somewhat deeper bowl of 1.11 angstroms. And this means that these molecules will undergo a dynamic behavior of a bowl-to-bowl inversion. And we are interested in examining this bowl-to-bowl inversion more closely and possibly catalyzing it with a pristine graphene sheet. So it should be mentioned that catalyzing these bowl-to-bowl inversions has attracted considerable attention in recent years. So for example, in this Nature Chemistry paper, they were able to show that the bowl-to-bowl inversion in corannulene can be catalyzed by passing it through a cyclophene receptor, and this is called induced fit catalysis. And the bowl-to-bowl inversion in sumanine has been shown to be catalyzed on a silver surface. So this naturally raises the question, can we catalyze these bowl-to-bowl inversions on a pristine graphene sheet? Let's examine the uncatalyzed corannulene bowl-to-bowl inversion. Here we have the reactant and the product, and we can see that these two can be interconverted between each other through a completely planar transition structure. We calculate a reaction barrier height of 47.3 kilojoules per mole for this conversion, which is in excellent agreement with the available experimental reaction barrier height of 48.1 kilojoules per mole. For sumanine, we have a very similar potential energy surface. Here we have our reactant sumanine bowl and the inverted bowl product, and they can be interconverted between each other through a completely planar transition structure. We calculate a reaction barrier height of 85 kilojoules per mole, which is basically spot on the experimental barrier height of 84.9 kilojoules per mole. Again, this very good agreement between theory and experiment gives us confidence in the levels of theory that we are using here. As we have just seen, these bowl-to-bowl inversions involve non-planar reactants and products and planar transition structures. So we would expect that these inversions will be catalyzed by pristine graphene because the pi interactions between the substrate and the two-dimensional catalyst will be maximized when the substrate is planar rather than when it's not planar in the reactants and products. For the uncatalyzed bowl-to-bowl inversion in corannulene, we obtain a reaction barrier height of 47.3 kilojoules per mole, and this reaction barrier height is reduced by almost 50% to 26.2 kilojoules per mole by placing a large graphene nano-flake catalyst underneath the corannulene bowl. An interesting point here is that the product complex is more stable than the reactant complex by 13.1 kilojoules per mole. This is because the pi system inside the bowl is smaller than the pi system outside the bowl, which results in larger pi-pi interactions between the catalyst and corannulene in the product complex. For the sumanine bowl-to-bowl inversion, we obtain a very similar potential energy surface. For the uncatalyzed inversion, we obtain a reaction barrier height of 85 kilojoules per mole, and for the graphene catalyzed inversion, this reaction barrier height is reduced by over 50% to 39.2 kilojoules per mole. Again, we see that the product complex is more stable than the reactant complex by as much as 34 kilojoules per mole. Again, this is because the pi system outside the sumanine bowl is larger than the pi system inside the sumanine bowl. So far, we have seen that a pristine graphene catalyst can catalyze chemical processes that proceed through a planar or nearly planar transition structure. This is because the planar catalyst stabilizes the planar transition structure to a larger extent than it stabilizes the non-planar reactants and products. But what about other 2D materials? Could other planar 2D materials catalyze the same chemical processes? For answering this question, we would like to consider 2D materials with significantly different electronic structures and chemical compositions than graphene. Here we will consider hexagonal boron-nitride and graphane. Hexagonal boron-nitride is an inorganic two-dimensional material. It still has a pi system, but in contrast to graphene, which involves homonuclear CC bonds, hexagonal boron-nitride involves polar boron-nitrogen bonds. Graphane is a fully saturated version of graphene. It involves only sp3 hybridized carbons, and it has vertical CH bonds above and below the molecular plane. Here we see the species located along the catalyzed Corannulene ball-to-ball inversions. We can see that an HBN and a graphane catalyst both result in very similar reactant complexes and transition structure complexes to those located along the graphene catalyzed Corannulene ball-to-ball inversion. Here we see the Gibbs free potential energy surfaces for the Corannulene ball-to-ball inversion. For the uncatalyzed inversion, we obtain a reaction barrier height of 47.3 kilojoules per mole. As we have already seen, this reaction barrier height is reduced to 26.2 kilojoules per mole with a graphene catalyst. Interestingly, with an hexagonal boron-nitride catalyst, we obtain an even lower reaction barrier height of 19.4 kilojoules per mole. As we might expect, with a graphane catalyst, we obtain a smaller catalytic enhancement and a reaction barrier height of 33.9 kilojoules per mole. Let's examine the nature of the non-covalent interactions responsible for these catalytic enhancements. Here we see the differences in electrostatic, dispersion, and Pauli repulsion interactions between the transition structure and the reactant complex. So, for example, this negative number means that electrostatic interactions stabilize the transition structure by 30.7 kilojoules per mole more than they stabilize the reactant complex. Overall, we see that graphene and HBN both results in similar electrostatic and dispersion stabilization energies, and also in similar Pauli repulsion destabilization energies. For a graphene catalyst, as we might expect, we obtain smaller electrostatic and dispersion stabilization energies of the transition structure, but also a smaller Pauli repulsion destabilizing energy of the transition structure. Overall, in all cases, the stabilizing dispersion and electrostatic interactions outweigh the destabilizing Pauli repulsions. So let's conclude. We have used DFT and double hybrid DFT calculations to show that pristine two-dimensional materials can catalyze a range of chemical processes, all of which involve non-planar reactants and products and planar transition structures. In particular, we have shown that these 2D catalysts can catalyze the racemization of binaphthyl and BINOL and the ball-to-ball inversion of corannulene and sumanine. The racemization of BINOL on a single-layer graphene has also been recently confirmed experimentally, which is a very exciting result. And we have shown that these catalytic enhancements are driven by electrostatic and dispersion interactions. With that, I would like to thank the ACS conference organizers for organizing this virtual conference under the current circumstances. I would also like to thank the Physical Chemistry Division for the JPhys Chem A Lectureship Award. I would like to thank the Australian Research Council for funding this research and the National Supercomputer Facilities for providing the computational resources. This is the group at the moment, And most of the work that I've shown you today was done by Asia Kroger, a PhD student. And most of all, I would like to thank you for your very kind attention.